When we consider the ionization energy trend across the period, there are two factors that we need to consider, and that is effectively nuclear charge and the atomic radius. And let's see how these two change across the period. The effective nuclear charge of sodium, we'll use the third period as the example, is +1, right? +1. Magnesium +2, aluminium +3, +4, +5, +6, +7, +8. It's increasing. Atomic radius, it decreases across the period, right? Let's see how this affects the ionization energy by actually applying this. Let's try and draw what these look like. What these look like on each of the atoms. So I'll just draw the outermost electron shell, and let's say sodium is like this. Okay, that's the outermost electron. Magnesium will have a smaller outermost electron shell, but it will have two. And then aluminium will have a smaller one, right? Let's illustrate this using these three examples. And then let's mark the effective nuclear charge. We have +1 for sodium, and +2 for magnesium, +3 for aluminium. Now I'm going to mark the electron being lost. We only have one in that sodium, and this one, and this one. Let's try and see which of these three electrons are the most strongly held. And it's obvious that the aluminium electron is the most strongly held because it's closest to the nucleus, and the nucleus is the most positive. So we can establish that across the period, the general trend is that the ionization energy is increasing. Okay? So let's go through the ionization state of each atom one by one, but then at the same time, let's consider the energy level diagram for each electron being added. Okay? So the y-axis is the energy level. Okay? And then here we're going to display the 3s orbital, and on the top we will display the 3 of the 3p orbitals. Okay, so the single outermost electron of sodium will be filled at the 3s orbital according to the Aufbau principle, right? So, and let's roughly designate the ionization energy of sodium to be around this place. Okay. The additional electron belonging to magnesium will also be filled in the 3s orbital in the opposite spindle direction, like that. Okay. And magnesium will have a higher ionization energy than sodium. So let's put it here. Now, the additional electron belonging to aluminium will be the first electron to fill a 3p orbital, like here. Okay? And according to our general trend, the aluminium should have a higher ionization energy than magnesium, so somewhere like this, right? But then let's consider the energy level of the 3p orbital in comparison to 3s. 3p orbital is at a higher energy state than 3s, meaning the electron inside that is also at a higher energy level. And that means it basically means that the electron is more excited. It's got more energy, it's vibrating faster. It requires less energy to remove this electron, push this electron to infinity than a 3s orbital, which means the energy required to ionize this outermost electron of aluminium is smaller than that of magnesium, giving us making the ionization energy of aluminium slightly less than that of magnesium. So let's cancel that one. Okay, so this is one exception to the increasing ionization energy trend across the period. According to the Pauli exclusion principle, the next electron belonging to silicon is not going to fill here, but then it will fill in the next unoccupied empty orbital, and it will give the silicon a higher ionization energy than aluminium. The next one also filling the next unoccupied orbital. Phosphorus ionization energy being the highest so far. And the next electron belonging to sulfur is the first electron to actually come into a already occupied 3p orbital here. Now, this p orbital is already occupied by the same negatively charged electron, which means there's bound to be some sort of electrostatic repulsion between the already occupying electron and the new incoming electron. And this repulsion makes this electron also a lot easier to remove. Just needs a little bit of a push to get this already repulsing electron removed to infinity, making sulfur's ionization energy slightly less than phosphorus. The next electron belonging to chlorine will fill this orbital, and it will be at a higher ionization energy level. And finally, the final electron filling the third energy level belonging to argon will make argon's ionization energy a lot higher than any of the rest, and that is because argon is group 8. It has full electron, the outermost electron shell is already full, and obviously doesn't want to lose that, so removing an electron will be very difficult. So the ionization trend across the period is that generally it increases across the period, with two exceptions, going from magnesium to aluminium, group 2 to group 3, and from phosphorus to sulfur, group 5 to group 6.